Welcome to Lecture 22 entitled Overview of Helmholtz Theorem, Divergence Theorem, Stokes Theorem, and Fundamental Theorem of Line Integrals. The material in this lecture is coming from Reading Assignment 4, the Introduction to Section 4, Part 4, and Section 4.5. The objectives are an overview of the theorems used in the remainder of this reading assignment and the geometrical and mathematical relationships. The specific concepts and visualization skills that we're looking at here include basically the Helmholtz decomposition theorem. What does it actually mean? How is it stated? The divergence theorem in 3D and Green's flux theorem in 2D. Followed by Stokes theorem in 3D and Green's circulation theorem in 2D. In fact, the flux theorems are essentially the 2D analog of the divergence theorem, and circulation theorem is the analog of Stokes theorem, but in 2D. And then the fourth item, the fundamental theorem for line integrals for any rotational field either in 2D and 3D, source-free field in 2D or source-free field in 3D. Now I just mention here in blue that in this course we will not cover the fundamental theorem for integrals and Green's theorems for circulation flux due to lack of time, and so you're not responsible for this material. Alright, so let's just look at the outline for this particular lecture. First thing we'll be looking at the preliminaries to the Helmholtz decomposition theorem, a 2D illustration. This is more or less just an extension to some of the material that was discussed. And then we'll look at the formal definition of Helmholtz decomposition theorem, particularly when we're dealing with 3D problems. And of course, we'll look at the geometric conventions for applying the divergence theorem, Stokes theorem, fundamental theorem for line integrals, just an overview. Then Stokes theorem, and then divergence theorem, mathematical form. These items that you noted here that are in a sort of a light orange color, we'll not be covering in this course. You can also basically essentially say that to a certain extent that applying the fundamental theorem for line integrals also is not considered part of this course, even though I haven't mentioned it in orange. Then we'll talk about some summary of some key definitions, and we'll just do a quick recap of what we've done so far in the course, and then basically discuss what will happen after reading week. So as I mentioned before, the items marked in light orange are not part of this course, but have been included in the videos. And item 12 is normally not stated in textbooks, but is an extension of the 2D case in item 11 to the 3D case. Alright, so this is the preliminaries to the Helmholtz decomposition, and we're using a 2D illustration because this is something that basically we had that we developed. Much easier to work with this to sort of use it as a sort of a means of describing the 3D case. So we mentioned much earlier that any vector field is a superposition of a field which is circulation free. This is a field we have that has only a flux, and a field which is source free, which is a field that only has a circulation component. And that the superposition of these two fields in general is any type of field that you can possibly imagine. In 2 dimensions, we basically would have a vector field of this form, where the x component of the field only has an xy component, and similarly the y component only has xy component. And there's no z component. Now the reason we're doing this is because we're going to try to make use of an operation that's typically done in 3 dimensions, but we'd like to apply it to 2 dimensions in order to extract some results. And so this is a sort of a simple way of casting a 2D problem in a 3D framework. Alright, so if we were to take the curl and divergence of F circulation, alright, which is what I'm done here, I take the divergence of the circulation component. If I do that, basically the divergence operation involves taking the derivative with respect to x for F and with respect to y. But because because we're dealing here basically with circulation, means the divergence will be equal to 0. On the other hand, the curl basically will be non-zero, and we give it a separate designation. We said it's a new vector field, jx of y. And if you take the curl, then you'll end up basically with this expression here. I've marked it in yellow, and in fact what I've done basically is use the determinant operator operating on the vector field and the partial derivatives. So partial x, y, z, and then f, x, y, g, 0. If we do basically the determinant of this, we'd end up basically with the expression that you see here. Now, of course, you would ask yourself the question, z hat. You know, there is no z hat if we're dealing with pure 2-dimensional problem. And so this is an example where basically what we have to do is to create a new entity which we call a fictitious vector, an imaginary vector, or pseudo-vector. And that pseudo-vector basically is pointing in the direction of the axis of rotation. All right. And so this is a way of being able to sort of describe something which doesn't exist in Z by just giving it, signing it in an imaginary direction. It's very similar to what you did with imaginary numbers, where you essentially said you can't plot it. But if you choose the y-axis, in a conventional xy plot to represent the imaginary axis, then in fact it's possible to basically draw a vector in the complex plane. And this is a sort of a similar idea, that we have to create a fictitious vector. Now, if we're looking at the flux, this is a simpler case. Divergence of flux, basically, if we're dealing with this case, then this will take on some scalar value, and just call it rho of x of y. And if you just write it out, similar to what we saw over here, this is just dfx plus dgy. But in this case, basically, the curl will be equal to 0. Here, basically, the curl was non-zero. Here, the curl was equal to 0. So essentially, these are mutually orthogonal to each other. You cannot create one, take one and make the other out of it. They basically are mutually exclusive of each other. Anyway, so this is basically our starting point, which then basically allows us to sort of formulate the Helmholtz decomposition for the general 3D case, which is basically what we will do next. All right, so now let's look at the 3D case, which is generally the one we're interested in. And so we now introduce a formal definition of Helmholtz decomposition theorem and the actual calculation of the flux component and the circular portion of the vector field. So in a very general sense, any vector field is a superposition of a field which has got pure source type behavior and pure circulation type behavior. And what we're saying is that the field which has pure source type behavior can be expressed in terms of the gradient of some scalar function phi. Now the minus term is here purely by a convention. Now this is typically the way it's written. And then the second term is the curl of some vector field A, and this basically represents the circulation component of the field. We call phi a scalar potential, and we call the A a vector potential. Now the other thing is some nomenclature. F flux, which is the field which is purely of a source type, has pure source type behavior. We call this an irrotational field. In other words, no rotational component, but also it's called a conservative field. And this has partly to do with the fact that this has been borrowed from the physics when we talk about conservative fields. F circulation, typically, which is the circulation component of the field, is called a solenoidal field. And this is one we refer to as a source-free field. This is purely rotation. Now, we perform a little bit of a trick here now. What we do is we take this general expression, which involves the superposition of two fields, and we take the curl of this field and the divergence of the field. And so if we take the curl of the field, then the curl of F would be equal to the curl of minus grad phi, right, plus the curl of an A, right? So if we take the curl of the flux vector, okay, then this term was equal to 0. I mean, we've shown in a vector identity in the last lecture, if you take the curl of the flux component, which is this one, right, then this term is identically equal to 0. On the other hand, if you take the divergence of the circular component of the field, which is one described by the curl of the vector potential A, the divergence of that will also be equal to 0 according to a vector identity, which we described in a previous lecture. So these are generally terms that we can state right off the hand. Now, there's a question that comes up in terms of, well, if given a field, how do I compute F flux and F circ? Well, what we'd like to be able to do is compute phi and compute A. If we know what phi is, then we can compute F flux. If we know what A is, we can compute F circ. Unfortunately, there are an infinite number of ways to select phi and A given a specific field F. The question then becomes, how do we obtain a scalar potential and a vector potential, and under what conditions are the solutions unique? The answer to this is partly provided in section 4.6, but you're not responsible for this. We're just basically stating it up front that there are ways to go about determining what phi and A are. F flux and F circ can be computed, as I mentioned, once phi and A have been computed. All right, again, I mentioned that any scalar multiply of grad phi is still an irrotational field, and the -1 factor is there by convention. All right, so now let's look at a sort of a geometric overview of the different theorems, followed by the actual mathematical expressions. So when we're looking at the divergence theorem, we're looking at two cases. One is the divergence theorem in 3D, and an equivalent to divergence theorem in 2D. For the 3D case, the convention is as follows. We always talk about a closed surface. So the diagram on the right shows a closed surface, and that we can identify differential surface area on that closed surface at each point on the surface. And that differential surface area is the unit vector that's normal to the surface, ds. So this is actually the magnitude of the differential surface area. This vector, by convention, must be pointing outwards from the closed surface that encloses the volume. dV represents the differential volume within this volume enclosed by the surface. In 2D, we're talking about a contour which is enclosing an area. So in this case, basically what we're looking at is the normal to this contour, which is shown here, right? And it's assumed that when we do an actual integration, we're integrating in a counterclockwise direction around the contour. Well, these are things to keep in mind. We're going to be mostly focusing on the divergence theorem in 3D. All right, so what about Stokes' theorems? Stokes' theorem is a little bit different, and so let's illustrate this using two specific cases, the 3D case and the 2D case. So the 3D case, basically, I've got a little picture here on the right to depict what is going on. So let's look at the individual items here. First of all, is that the orientation vector for a differential area on an open surface. So open basically means that it doesn't bound a volume, it's just an open surface. And it's bounded by a closed contour, and it points in a direction consistent with the right-hand rule. All right, and so here is the contour that you see, this red one. And you see I'm traversing the contour in this case in a counterclockwise direction. I could also go in a clockwise direction if I want, but it's a counterclockwise. So we see that this is an area that's bounded by the contour, which is planar, but we also see that this hemisphere is also bound by the same contour. And so there's actually no limit in terms of the number of possible surfaces that we can generate which are bound by the contour. But the main thing is to realize that the differential surface area associated with the contour is basically by right-hand convention. And so if you take the fingers of your right hand, point them in the direction in which you go around the contour, and the thumb points in the direction of the differential surface area vector. So for the planar case, it would be this arrow, and for the hemispherical case, it would be the arrow that you see here. And of course, it will change its orientation as you move back and forth along the hemispherical surface. So these first 3 points here, or these first 4 points, basically summarize what we've just spoken about. Now in 2D, of course, we have the same problem, is that you still use the right hand, but the thumb points in the direction of the axis of rotation, which also represents the differential surface area. But of course, in 2D, the z-hat direction does not exist, so we just artificially give it a label J, which is a pseudo vector, which happens to be aligned with the z-hat direction. So these are the takeaway messages regarding how to assign directions. That it is what's the relationship between the direction of the tangent vector and the normal to the surface area, this surface area being one that's bound by the contour. Now for line integrals, and we're not going to be dealing with this in class, but just very quickly talk about it. We have basically a source-free field, and we have an irrotational field. And so for the source-free field in 2D, we're looking at just a line segment here. We're following this line segment, and we look to our right when we're basically traversing a closed contour. So this is a differential surface. And so this is, again, convention-wise, you always make sure it's pointing to the right. A rotational field, here it really doesn't matter if it's 2D or 3D, because essentially in 2D we're just looking at following this contour in the 2D plane, whereas here we're following a contour in three-dimensional space. All right, what about Stokes' theorem in mathematical form? This is the 3D case. And so now we basically look at mathematically the relationships, again making use of the diagrams I just shown earlier. So this is essentially the relationship. It says if you take the vector field, some arbitrary vector field, dot product at every point on this contour with the differential tangent vector, and integrate around that closed contour, that's equivalent to taking the curl of the vector field at each point on a given surface. And here I've shown two example surfaces, both bound by the same contour. So it could be the planar surface or hemispherical. If I take the curl of the vector field, dot product with the differential surface, and integrate over that open surface, that's equivalent to taking the vector field, dot product with the tangent vector, and integrating around the contour. Now I could either choose the planar surface, which would be this integral, or I could have chosen the hemispherical surface, which is this one, and I'd end up with exactly the same result. So this gives me a degree of freedom where I can choose an area to my liking, do this calculation, and given that these two surfaces both share the same contour, I'd end up with the same answer. So this is something to keep in mind, because when we get to reading assignment 5, we'll be applying this theorem to deal with the solutions to some physical problems. All right, what about the divergence theorem, the mathematical form? Again, we know that we have a closed surface, and we also know that the differential surface area associated with the surface must be pointing outwards from the surface. All right, so here's the mathematical form. What it's essentially saying is that if you take the dot product of the field and the differential surface area vector at each point on this closed surface and integrate that resultant scalar function over the full surface, that's equivalent to taking the divergence of the vector field at each point within the volume bound by the surface and integrating this scalar function over the volume. These two are equivalent to each other. Right, and so just make sure that you realize that there is this difference between the divergence theorem and Stokes' theorem. Divergence theorem deals with closed surfaces. Stokes' theorem deals with open surfaces. The divergence theorem, it's always a vector pointing outwards from a closed surface, whereas for Stokes' theorem, it's a vector that's pointing in a direction consistent with the right-hand rule. So they are very different. Just make sure you remember that. All right, so we can also look at the 2D equivalent of Green's circulation theorem, which we call Green's circulation theorem. That's the 2D Stokes theorem. In this case, we would be dealing with contours and areas. And so here we go, if we're going around the contour in a counterclockwise direction, we take the dot product between the tangent vector and the field. That's equivalent to basically taking this scalar function, and these are basically derived from the vector field itself, and then integrating this scalar function over the area enclosed by this contour. This is basically called Green's circulation theorem, or equivalently it's Stokes' theorem in 2D. Again, the right-hand rule applies. We can also look at the 2D version of the divergence theorem, which we call Green's flux theorem. So in mathematical form, again, we're traversing a contour in a counterclockwise direction, which means the normal vector points to your right, which means it's pointing outwards from the contour. In 3D, it was pointing outwards from a surface. In 2D, outwards from a closed contour. In this case, we're taking the field vector at each point on this closed contour, dot producting it with the normal to the contour at that point, and then integrating over the closed contour. That's equivalent to taking the partial of the x component of the vector field plus the partial of the y component of the vector field to this scalar function and integrating over this whole area which is bound by the closed contour, and these two are essentially equivalent to each other. Again, this is Green's flux theorem, which is equivalent to divergence theorem in 2D. All right, so then we have basically the fundamental theorem of line integrals for rotational fields, and so we have 2 points, and we're going to integrate between A and B. And if it's an irrotational field, then we can basically describe the field as being a gradient of some scalar function. This is something we've shown earlier when we talked about the Helmholtz decomposition theorem. So if we basically substitute F flux into this expression here and integrate between point A and point B, we find out that's equivalent to evaluating the scalar function at point B subtracted from the scalar function evaluated at point A. That's basically this result. This is the resultant that you get, given the fact that F flux is the gradient of a scalar potential. This is a fundamental theorem for line integrals for a conservative 2D or 3D field. We can also look at it for source-free field in 2D, but in this case we define what we call a stream function. And the stream function takes on the field, which is purely of a rotational form, in terms of stream function would take on this form. So given a stream function, if we take these partial derivatives, we essentially are creating a field which basically has pure circulation characteristics. That means it's source-free. In this case, if we take the dot product between this vector and the normal to the contour going from point to point A, this is equivalent to evaluating the stream function of B minus the stream function of A. Okay. All right, and the last one would be the fundamental theorem of surface integrals for source-free 3D fields. So in mathematical form, basically, we'd have a contour, as shown here. But what I've done here is basically I have an upper surface and I have a lower surface. All right, so as far as the circle here, for instance, fcircle.nsds, if I basically were to apply this theorem here, I can basically use Stokes' theorem to convert a field into the curl of a vector field. So this is basically fcirc is the curl of the vector A if we're dealing with a field which is basically source-free. I can make this automatic substitution. However, this expression, right, in this form can be converted into a closed contour line integral using Stokes' theorem. So from here to here is basically just applying Stokes' theorem, right? And so this is a fundamental theorem of surface integrals for a source-free 3D field. In 2D, basically, we're dealing with a contour. In this case, we're dealing with a surface. All right. Also, you'll notice here, again, it does not depend on the shape. So if this is a surface integral, this is a line integral. So this line integral could have this surface or could have had this surface. Why? Because we're making a comparison to the same contour that we see here. This, by the way, the vector potential A will be investigated in EC221 next semester. All right, so let's basically now just summarize some of the key definitions. Some of this material basically is not necessary as part of this course, but we're basically reviewing all the bits and pieces. And so I've just basically itemized everything here. So the first thing is that a vector field is comprised of a component f of flux, which is irrotational, that's a vector field, and a component f circulation, also a vector field, which is source-free. And so this is just some of the typical words that are used to describe these different types of fields. A vector field which is rotation-free, also called irrotational, is defined as a conservative field. It's just a label that's given. It's given for historical reason having to do basically with potential fields like the field of gravity. Secondly, that a vector field which is source-free is defined as a source-free or solenoidal field. That's, again, a word that's typically used to describe a source-free field. All right, if we're dealing with a source-free field, that's F is purely a circulation, fcirc, then it's defined by the vector equation curl of some vector potential A. And depending on whether you're dealing with 2D or 3D, basically A takes on a different form. If it's a 3D problem, then basically A, the x component, y component, and z component are basically functions of x, y, and z. On the other hand, if we're trying to sort of mimic the curl operator in 2D and allow it us to basically do some computations in 2D, then basically the vector field A has to have the form that's shown here. That is the x component 0, the y component 0, and the z component basically A of z. This basically could only be function of x and y. So to create a 3D vector field, we need to basically use the curl operator to exploit it. So that basically summarizes why A of z is only a function of x and y. An irrotational field, that is F is equal to F flux, is defined by a vector equation gradient phi or scalar multiple thereof. Typically there's a -1 put in here, basically because the theorem itself that we dealt with, which is the Helmholtz decomposition theorem, basically assumes a value of minus there. 5xyz is defined as a scalar potential in 3D, and phi xy is defined as a scalar potential in 2D. All right, so here now what I've done is just summarized everything. Again, we did not basically deal with this material here in the course, but I've basically summarized it. What we're saying basically is that if you basically take a closed contour integration, that is, you go basically calculate a circulation between A and B, and then go from B back to A, that means you're doing a full circle. All right, you'll find that basically this value will be equal to 0. Okay, that's equivalent to saying that the closed contour integral of f dot ds equals 0. For a source-free field, the only difference in this is that the TDS gets replaced by NSDS, which is the normal to the contour. So we're going from A to B, followed from B to A, and forming a closed contour path. In the case of source-free field, this integral is always equal to 0. In the case of 3D, we're dealing with surfaces and not contours. In this case, basically a closed surface. Right, potentially could be essentially the summation of a number of discrete surfaces. Here's an example, just two surfaces. There's an upper surface and a lower surface. And so this would be a contribution of an upper surface and lower surface. If you stitch the two together, then basically this is a closed contour. And this is basically saying the total flux. This is basically the total flux over closed surface. All right, so we can basically also write this out in this particular form, basically using Stokes' theorem, and this is something we're going to be showing. That this can be represented by the field here, basically, because it's basically a field which has only got a source. That means the circulation component, basically F here, can be represented the curl of A. And so this is basically substituted in this case, and substitute in this case. And then the Stokes' theorem basically allows us to convert a surface integral into a contour integral. It takes on this form here, and it turns out basically that one of the contours moves in one direction and the other contour is in the opposite direction. So when you take the summation of these two contributions, the value is equal to 0, which essentially tells you that the closed contour integration over a surface, closed surface, in the case of a source-free field, is equal to 0. And so, this is the 3D case, this is the 2D case, and for conservative fields, basically this applies for either 2D or 3D. All right, so let's recap the past. Where are we? And then, of course, where we're going to go. So what have we done so far? Well, we did differentiations and limits, and most of this material basically came from the textbook and extracts from reading assignments 1 and 2. And these are the specific extracted lectures that we were looking at. And we dealt with partial derivatives, chain rule, gradient directional derivative, tangent plane, and small signal modeling. We then moved into integration and limits. And again, in this case, it's the textbook and reading assignment 3, short. In this case, we looked at double and triple integrals in Cartesian coordinates. And then basically we showed that it's possible to work in other coordinate systems because conceivably it makes the integrations that much easier. And so we had to basically describe what we meant by change of variables and give some examples, the most common ones being in 2D polar coordinates and in 3D cylindrical and spherical coordinates. And this material basically was covered in lecture 12. And integration involving contours and surfaces in 2D and 3D, this is extracted from reading assignment 4, short, and these are basically the contents of lectures 17 through 20. So we did contour integrals and surface integrals. In lecture 21, we introduced the concepts of flux and circulation. And also from this, we came up with the definition for the divergence of a vector field and also the curl of a vector field. In both cases, it involved taking limits. And then basically, we just have vector calculus theorems involving contours, surface, and volume integrals. And this is again from reading assignment 4 short. And we've just described the overview of the Helmholtz decomposition theorem, divergence theorem, and Stokes' theorem, and this basically is contained within lecture 22. All right, and so basically we are now at a point where reading week is upon us, and so where are we going to go after this? All right, so here basically I've just shown you what's left for the rest of the course. On this side, which assignments we're considering, and on this side basically the extracted lecture notes which are relevant. And so for the divergence theorem, we're going to be looking at sections 4.11, 4.12. This is basically to look at some examples of how the divergent theorem can be applied, but these are problems involving just sort of a geometrical nature. Similarly with Stokes' theorem, this is sections 4.21 through 4.23, and these basically deal with lectures 23 and 24. And then we move over to reading assignment 5, short, and this is introduction sections 2. This all material is basically contained in lectures 25A, 25B, and 25D, and this is the only material that you'll need to look at. Reading assignment 0, these basically we've extracted sections 4.2, 5.2, 5.3, 6, 8, and 9. And there are also some self-study archived lecture video 1C if you wish to look at on vector transformations. But all the information you need with respect to this course is contained in lecture 25C. Again, these are the extracted notes. And then for reading assignment 5 short, we're going to look at the introduction to section 3 and section 3.2, which is basically the subject of lectures 26 and 27. You will have to review the geometry for which you'll be tested in quiz 10, and for this you need to refer to table 3 in the lecture quiz schedule assigned homework problems document. And section 3.5 gives some example problems suitable for testing purposes. And then reading assignment 5 short, we'll be looking at problems involving circulation, and here we'll be looking at the introduction to section 4, sections 4.1, 4.2, and 4.3, and this is the subject of lectures 28 through 30. That is the extracted notes. And if you look at section 4.6, you'll see some example problems that are suitable for testing purposes. You may also find the online archive tutorial videos for basically these two sections helpful, and these are contained within videos 9, 10, and 11. All right, so this concludes lecture 22. Thank you for listening.